Welcome back to the Deep Dive. If you need that shortcut to being truly well-informed on a complex topic, this is where you land.
Today we are taking quite a fascinating journey.
We're unpacking the core mechanics of how a machine actually learns to see. We are going deep into computer vision, tracing the evolution from really the absolute simplest functions all the way to convolutional neural networks, or CNNs.
We've put together a really brilliant collection of source material for this deep dive. It's the foundational stuff, the concepts that underpin modern visual AI.
And our mission here is to get past the buzzwords and give you the math, and I think more importantly, the intuition behind the algorithms that are powering, well, everything.
Everything from self-driving cars to facial recognition.
We're going to start with the basics, linear classification, how a computer first tries to score an image. Then we'll get into the puzzle of how it learns the right scores, so the mechanics of loss and optimization.
And finally, we have to talk about the fundamental limitations of that linear approach, which forces us to bring in nonlinear layers and ultimately the specialized components you see in CNN.
It's the story of going from a simple numbers game to a true layered understanding of features.
Exactly. And to start, we have to establish what an image even is to a computer. It's not a photo. It's just a stack of numbers.
Okay, let's unpack that fundamental translation. When you upload a picture of, say, a puppy, the computer doesn't see fur and a tail. What does it see?
It sees a massive array of numbers. I mean, think about a small image, one that's used in these training sets, maybe 32 pixels wide, 32 pixels high, and with 3 color channels, red, green, blue.
Okay.
If you multiply those dimensions out, you get 3072. That tiny little image is just flattened into one huge long vector. 3072 numbers. That is the input. That's our X.
And the model's first job, this linear classification, is to take that giant vector and turn it into a set of confidence scores. So if we have 10 classes, cat, dog, plane, it needs to spit out 10 numbers.
Precisely. And the core function that does this is 5x wx plus b db. The input pixels, your x, get multiplied by a set of learned parameters, the weights w, and then you add a bias, b.
And the result is those 10 class scores.
That's it.
That function looks deceptively simple, but understanding what it represents is key. You mentioned there are 3 viewpoints that really help with intuition. What's the first one?
The first is the algebraic viewpoint. This is just pure matrix multiplication, no mystery. The 3072 inputs are multiplied by the weight matrix, W. Each row in that matrix produces one of the 10 final scores.
So it's literally a weighted sum of all the input pixels.
Just a linear combination, massive, fast arithmetic.
Okay, but that's not very intuitive. The second viewpoint, the visual viewpoint, is much better for picturing what's happening inside the machine.
This one is fascinating, yeah. It gives the weights, W, a physical meaning. Think of that weight matrix as holding 10 different templates, one for each class. So if you visualize the numbers in the cat row of W as if they were an image, it would look like a blurry average cat. The plane row looks like a blurry average plane.
So the classifier isn't really analyzing structure, it's just doing a comparison. A new image comes in, and the calculation is basically asking, how much does this new image look like my blurry cat template?
Exactly. And how much does it look like my blurry dog template? The one it resembles most, numerically, gets the highest score. It's just correlation, a very fuzzy comparison machine.
Which brings us to the third viewpoint, the most abstract one, but the one that shows the model's limits, the geometric viewpoint.
Right. This is where we have to think in high-dimensional space. We're not talking about a 2D graph. We're in a 3072-dimensional space defined by those input numbers.
And in that crazy space, what's the classifier doing?
It's drawing straight lines, or what we call hyperplanes. These are the decision boundaries. The model is literally carving up the data space and saying, everything on this side of the line is a cat and everything on the other side is a dog. The linear function guarantees those boundaries are always straight.
Okay, so we know how it scores an image, but we start with those weights, the W being completely random. How does the machine get from random noise to those perfect blurry templates?
Well, that is the entire training process. And it all starts with the loss function, which we call L.
The loss function.
We need a way to measure how unhappy we are with the model's current guesses. If the current weights give a high score to dog when the image is clearly a cat, the loss function spits out a really high number. The goal is to find the weights that make that number as small as possible.
That makes perfect sense. It's an unhappiness meter. And the source materials say the full loss is a balance between 2 things. The first is data loss.
Right. The data loss measures how well the model fits the actual training examples. And we see 2 main types. One is softmax loss. The idea behind softmax is it takes the raw scores and sort of squishes them into something that looks like a probability distribution.
So it forces the model to be really confident. If it's a cat, the softmax loss pushes the cat score to be exponentially bigger than all the others. It drives that probability towards 1.
Exactly. The other big one is hinge loss, which comes from support vector machines. It's a bit different. It's not about probability. It's about having a margin. It's very unforgiving.
How so?
It doesn't just want the correct score to be higher. It demands the correct score be higher by a specific amount, a margin, usually 1. If a wrong score gets too close to the right score, the model gets penalized. A lot.
So data loss is about getting the answer right. But then there's the second component, the regularization loss, RW. This is about penalizing the weights themselves. Why?
To prevent overfitting. Imagine a model that just perfectly memorizes every single training image of a cat. It would have 0 data loss. But then you show it a new cat, one it's never seen, and it would have no idea what to do.
It is generalized.
Exactly. Regularization penalizes weights that get too big or complex. It forces the model to find simpler, smoother, more generalizable boundaries. So the full loss is just the average data loss plus this complexity penalty.
And once you have that single unhappy number, the process of optimization begins. This is the search party trying to find the minimum L. The most basic search algorithm is stochastic gradient descent, or SGD.
SGD is the fundamental move. It calculates the slope of the landscape right where we are, and it takes a tiny step straight downhill. The gradient tells you the steepest direction down.
But just taking one step based on the local slope can be slow or get you stuck. The sources mention more advanced optimizers to SGD with momentum, RMS prop, Adam. What's the idea there?
They're just smarter ways of taking that downhill step. They don't just look at the immediate slope. They have memory. Momentum, for instance, gives the searcher some inertia. If you've been rolling downhill fast in one direction, you keep going a bit.
Letting you roll over little bumps in the road?
Right. And something like Atom is even smarter. It adapts the step size, the learning rate for every single weight individually. It's a clever way to find the bottom of that valley faster.
And the engine that gives all of these algorithms their directions, the thing that tells them where downhill even is backpropagation.
Yes. Backpropagation is really just a clever application of the chain rule from calculus. It flows backward through the model to answer one question. If I wiggle this one specific weight, just a tiny bit, how much does the final loss change?
It's calculating influence.
Exactly. We talk about an upstream gradient, which is how the final loss affects a node. You multiply that by the local gradient, which is how the inputs affect that node's output. And you get the downstream gradient. It's a step-by-step backward flow of influence.
And for anyone getting lost in the math, there's one simple rule to hold on to. The gradient that you calculate must always have the exact same shape as the data it's influencing. If your input is a 3072 number array, the gradient flowing back to it is also a 3072 number array.
So we have all this incredible mathematical machinery to find the best weights, but here's the pivot, the really critical point. Despite all that, the simple linear classifier just hits a wall, a fundamental wall.
And that wall is power. They're just not versatile enough for the real world. Why do they fail so badly with real, natural images?
Well, let's go back to those viewpoints. Visually, they only learn one template per class.
That single blurry cat.
Right. If all your cats are facing the camera, it might work. But what if you show it a cat from the side? Or in a shadow? Or curled up in a ball? That one blurry template is suddenly useless. The variation is just too much.
And geometrically, they can only draw those straight, linear decision boundaries. The classic example of this is the concentric circles, right? A bunch of red dots in a circle surrounded by a ring of blue dots.
And there is just no way to draw a single straight line, a hyperplane, that can perfectly separate the red from the blue. It's impossible. The line just fails.
And that failure is why we have to move to neural networks.
Yeah.
Because we have to introduce the solution to this problem.
Nonlinearity.
We go from that simple function, 5 equals wx to a two-layer network. 5f kills w man x, 0 of w1x. The key is that piece sandwiched in the middle.
That max-ux function is the rectified linear unit, or ReLU. That's what gives us the bend. Before, everything was a straight line operation. But ReLU is simple. It just takes any negative value and sets it to 0. Visually, it's a bend line.
And that one simple bend, when you chain it with linear transformations, is a total game changer. It lets the model draw decision boundaries that are curved, or circles, or complex shapes. It solves the concentric circle problem immediately.
The whole structure changes. Your 3072 inputs hit the first weights, W1, and produce a hidden layer of features. That hidden layer gets filtered by the nonlinear ReLU. Then those results go into the final weights, W2, to produce the 10 scores. It's the depth plus the nonlinearity that creates the power.
Okay, so now we have basic neural networks. But for images, we need to go a step further to convolutional neural networks. CNNs aren't just general networks. They're built specifically for the 2D structure of an image.
That is the key distinction, yes. General networks use fully connected layers and activation functions like ReLU. CNNs add two new image-specific tools to the mix, the convolution layer and the pooling layer.
Let's focus on the convolution layer because this is where the magic of CNNs really is. It throws out that old, inefficient template matching for something much smarter. What's the intuition?
Instead of one giant blurry template for a whole cat, convolution uses tiny local templates called filters or kernels. Imagine a small 3x3 filter. It doesn't look at all 3072 pixels at once. It only looks at a little 9-pixel square patch at a time.
So the filter is like a little magnifying glass scanning across the image.
Exactly. And that magnifying glass is looking for one very specific thing. One filter might have weights that are perfect for detecting a vertical line. Another might look for a diagonal edge or a corner or a patch of green. It just slides across the whole image, doing that little multiplication on each local patch.
And every time the filter finds a match, like the vertical edge filter finds a strong vertical line, it puts a high number in the output.
Right, which means the output of a convolution isn't a single score. It's a new image, a feature map, that tells you where in the original image those specific features were found. You stack a bunch of these filters together, and the network learns these low-level, primitive features all by itself.
That is such a critical shift. We're not trying to match a whole cat anymore. We're breaking the image down into its parts. Lines, edges, corners, and then later layers can combine those to find more complex things like eyes and noses.
Which brings us to the pooling layer. If convolution creates these feature maps, they can still be huge. Pooling is just a way of aggressively downsampling them.
It shrinks the representation. If your feature map is 224 by 224, a pooling layer might shrink it down to 112 by 112. It's reducing the size, but keeping all the feature depth.
And this does two things. First, it reduces the amount of computation needed, which is huge. And second, maybe more importantly, it provides a bit of translation invariance. If that vertical edge moves over by a pixel, the pooling operation will still capture that it was there, making the network more robust.
This whole shift from one giant template to these localized learned features, it just highlights how revolutionary CNNs were. Because before this, engineers were spending their lives manually inventing these features.
That's the crucial contrast. When we only had the simple linear classifier, we had to invent the feature representation ourselves. We weren't just classifying the raw pixels. We had to extract features first, then classify the features. That feature extraction step was all human engineering.
The simplest version was something like a color histogram, just counting the colors. But for real object recognition, the solutions were incredibly complex.
Oh, yeah. The sources detail the histogram of oriented gradients, or HOG. This was a breakthrough, but the complexity was just staggering. They were measuring gradients, which are basically the direction of edges.
And the process was so specific. You divide the image into little 8x8 pixel regions. Then in each region, you'd calculate the direction of all the edges and sort them into 9 different bins.
Now think about the final output of that. For a medium-sized image, say 300 by 240, you end up with 40 regions across and 30 down. And each region has 9 numbers.
30 times 40 times 9.
You're feeding the classifier a feature vector with 10,800 numbers, all of it hand-engineered just to describe the edges in one image.
10,800 numbers. It's incredible. And there were other methods, like bag of words, where you'd pull out random patches and cluster them to create a codebook of visual words. All of it was manual abstraction.
The takeaway is the sheer amount of labor. Before CNNs, the success of your model depended entirely on how clever the human engineer was at designing that perfect 10,800 number vector.
So putting it all together, the story's pretty clear. We started with a linear classifier, which was just fundamentally stuck. It could only draw straight lines and use one blowy template per object.
And those limits forced us into this era of painstaking, handcrafted features like HOG, where people spent years trying to manually define what an edge was, creating these enormous 10,800 number vectors.
The move to deep learning and CNNs changed that whole game. By stacking layers with nonlinear functions, we solved the straight line problem. And by using convolution layers, the network just learned the features itself. It figured out that vertical edges are important without a human telling it so.
It learned to bypass that entire 10,800 number step. We've gone through the mathematical engine that lets it do this, from optimization, finding the path downhill, to backpropagation, calculating influence backward. And we saw that even 2 layers can solve the linear boundary problem.
But in the real world, in modern computer vision, we don't stop at 2 layers. We have architectures with dozens, even hundreds, of these nonlinear layers stacked on top of each other, truly deep networks.
And that's really the provocative thought to leave you with. If the first layers are learning simple features like edges, and the next layers combine them to find corners and textures, what are those 50th or 100th layers learning?
What kind of unseen, highly abstract, maybe even incomprehensible features is the network optimizing for?
What is the computer seeing that a human mind never even thought to label?
Something to think about until our next deep dive. Thanks for tuning in.